Hello.
Hey Zara, hey Zach, how's it going?
Good. How
Good,
are you?
good.
Yeah, not too bad, not too bad.
How's the new job, Karthik?
Very rainy.
The job is rainy?
Well, everything is rainy, so the job is it's
Okay.
starting to rain here and then it just doesn't stop. It's
In
just
the Pacific Northwest or something?
yeah, in Vancouver, so it's raining literally all the time. And yeah, that's I find that's just how it is for like, I don't know, 8, 9 months of the year. So yeah. Just gonna deal with it. But no, this job's been, nice. I've been just mostly making connections and meeting new people. So I'm not teaching this year. So just like setting up the lab and proposals and all of that.
Fun time to be submitting proposals. Maybe it's different in Vancouver.
It's slightly better here. Yeah, yeah, the administration is, I think, slightly more kinder than where you are. So
It's a nice way of putting it. Hey everybody, it's nice to see you all again.
Amy?
I think folks in our respect team never met Zach.
That's right. Hi, Zach.
So
Hey?
Zach has been working on the Illinois project and he's just contributed a lot of technical knowledge and detail about the operation of heat pumps, or non-operation as the case may be.
The limitations of heat pump operation.
Limitations. And yet he's installing an incredibly
Oh no,
complex.
they never got back to me.
They never got back to you. He's wishing for.
I have a complex heat pump system I'd like to put in my house, and it's probably never gonna happen.
I'd like to hear more about that.
Zach, can I interview you?
Sure.
You should do the next presentation next week in 11 o'clock.
Resident.
I got ghosted by a very reputable company out here.
Really?
Yeah.
Maybe it's because you're so shady.
That could be part of it.
Um, yeah, well, I want to let Kartik take the reins here. Oops, I need to enable sharing. Um, Kartik, I don't need to introduce you to anybody, but maybe you want to, it'll probably be in here too. But
Mhm.
your your expansion of direction is the topic here. So this is kind of a reintroduction of yourself.
Yeah, there's going to be a bunch of introduction
Oh,
slides
can
with
we should we record this? Oh, we are recording, right?
It
Yeah,
said that
I'm just
it's
gonna let it
recording.
roll.
yeah, okay, yeah, I think what I have today, this a bunch of introduction slides about my new lab. Feels weird to say, but yeah, I have a lab, hired a few students, so we're just getting started. So there's some ideas that are probably going to be an extension of, I think, what uh, you saw previously, but there's a bunch of other ideas, some chemistry in there, which I'll try to explain. And yeah, happy to discuss more potential things we can work on together. So just free-flowing discussion. So just stop me anytime or you can just save it till the end. I do have a reputation of not finishing all my slides, so I'll try to go quickly so that we have more time for talking than me just, yeah. All right. Okay. Yeah. So this is about absolute sustainability and how we are thinking about designing materials from right from the atoms all the way down to households and people using the technology and materials that that we develop in the lab. Right. So yeah, the big question that sort of drives the lab is how do we assess material sustainability? And the definition that drives this is designing materials and material systems for energy transitions while quantifying and integrating that impact that they have on humans into the design process. So I'll talk about examples in a little bit, but a lot of the times people in design are often blinded or do not have the necessary tools to think about impact, and we are mostly focused on efficiency gains. So a lot of the effort in the lab is to incorporate some of these impact metrics. I'll talk about what they are into the design process. So yeah, my lab is called like the Sustainable Materials Lab, or SMALL, and we are at the intersection of materials design, policy, thinking about environmental and well-being impacts. So the program and the different projects are trying to integrate these four foci into I know Tammy hates frameworks, but into a framework. So that's what we're
Why,
trying to
why do
do.
you think I hate frameworks?
I remember you saying at some point, oh, it's another framework paper, we don't want to do
No,
that framework.
I like frameworks.
Okay.
I just, I think we should observe the proliferation of frameworks.
Okay. So yeah, so a bit of background. So how did we get here? What happened? So I'll start off with this framework that I think Narsama put together a little while ago, thinking about how industrial supply chains and technology interacts with future material demand and how that has an influence on the climate and environment. So in the existing supply chain focus framework, which is where a lot of my training also happened, so designing materials, directly working with industrial supply chains. And if you look at future material demand under this paradigm, so here's one example looking at total material requirement on the y-axis for the next 3 decades. This is just focusing on transportation sector. What the predictions usually show is that there is going to be a decreased demand for coal and oil, both due to efficiency gains in gasoline engines, but also moving away from coal and oil to more EVs and using lithium and cobalt instant. And that's sort of reflected in the expected demand for these critical minerals as well. You can see this about 100% increase going from now until 2050 for the cobalt and lithium. And this is just for the transportation sector. And if you generally look at expected increase in demand for critical minerals, for lithium and cobalt, everything put together, you're looking at 400, 500, 1,000 for lithium as well. So there is going to be a lot of increase in demand for these materials, and we started to think about the consequences of such an increase in material demand, because the way impacts are generally thought about. So here's one example looking at environmental impacts on the y-axis. So these are just thinking about greenhouse gas emissions. And then social impacts coming with lowered well-being of those along the supply chains of these materials. So coal, oil, and gas are sort of in between. So they have reasonably high environmental and social well-being impacts. And when we talk about transition materials for more sustainable applications, lithium and cobalt are sold as being more sustainable because they have lower environmental impacts coming, because now you're not burning any more oil and gas, but we don't really account for social impacts associated with food insecurity, water risk, conflicts, a lot of these are usually qualitative and there's not much quantitative numbers associated with these transition materials. And this is the case for a lot of other such minerals as well. So here's another study looking at cobalt, and they find pretty high risk indices for water, food, and conflict. And same is the case for lithium and manganese, platinum, silver, all of these materials go into batteries, fuel cells, electrolyzers, a lot of technologies and materials that are usually sold as being sustainable, but when you look at other dimensions of sustainability, they fall pretty short. So if you go back to this framework, what we add is the next dimension of well-being of those along these supply chains who are impacted by future material design elsewhere. So that's the first connection that.
Narasimha's hand is up or was up. Do you want to take clarifying questions during
Yeah,
the
go ahead, yes.
presentation, Karthik? Or people can just shout out, I think, because
Yeah, of course,
it's
yeah.
hard to see hands from the
Sorry.
presenter.
Sorry, Karthik. Just on this one,
Mhm.
I'm just curious, some of the stuff you talked about, I mean, it's already, Kreutzig et al. Had already characterized lithium as high on the social adverse impacts.
Mhm.
But you're indicating that maybe it's still underestimated. Or are you mainly talking about y-axis, like water risk, for example? But some of the food insecurity conflict stuff,
Mhm.
is that already incorporated, or you think it's sort of underestimated in the current literature as well?
I think there's several problems. One is qualitative versus quantitative. So, for example, the Nature Climate Change paper, it was a bunch of experts who sat down in a room and came up with indicators and then ranked them, and that's how they have the social impact, the number where it is. So there's methods in that sense. And for example, the paper on the right, there is no spatial component, or the way they do the spatial analysis is very sketchy at best. So for example, what they do is they might have a mine location, let's say in Chile, but they don't have water risk associated for, let's say, a 10-mile or 10 some radius. So they'll use a national level indicator for a local problem. So there's the spatial component, I think, which I'll come to at a later point, but I think that's one of the bigger challenges, is not having enough spatial impact data. Right. So I think just to conclude this part, what we see is that sustainable transitions associated with energy, alternate energy sources, although they lower climate risk from greenhouse gas emissions, they seem to be increasing or creating new social risks associated with extraction and material poverty for those living in those extractive locations. So the question is, how do we get out of this? And there's been a lot of work on the demand side, trying to model if there are arguments to be made for decreasing material demand by focusing on solutions such as, in this case, for the transportation sector, increasing public transportation, increasing the service that people get rather than the material demand. So having more walking options, things like that, to decrease the demand. So although some of these ideas already exist, it is unclear if such ideas directly contribute to the well-being of those going through this decreased demand. So that's one question that I think got us a little more excited. So we wanted to see if there are ways to have higher well-being with lower material demand, because the argument is that we could lower both climate risk associated with greenhouse gas emissions, but also lower new social and environmental risks. So yeah, so can we have sustainable transitions with higher well-being and lower material demand? And how does one go about creating frameworks, methods, and making a case for this thinking? And at the same time, I mean, we've been talking so far about decreasing our consumption and figuring out ways to decrease material demand, but a lot of these aggregate metrics, as we all know, hide the extent of material poverty. So if you look at the definition for poverty in the United States, it is income-based, and it is the amount required in order to meet basic needs that people have. And then if you just look at the metrics across energy, food, housing, and mobility, energy stands at about 20%. So about 1 in 5 households in the United States are classified as being energy poor. Food is 10%, and there are no clear defined metrics to quantify mobility and housing as well. So there is a dual challenge here, not about just decreasing material demand, but also ensuring that our sustainability efforts reach those lacking access to these materials as well. So that, going back to the framework, I think that adds another dimension here, which is thinking about the direct connection between how household lifestyles and the way people consume things or not influences their well-being as well. And the goal of my program is to use the demand coming directly from the households to influence how we design materials, and flipping the narrative about how one interacts with industrial supply chains. So we want to make a case for future material design being driven by household demand, and how we could use that to influence industrial supply chains and the way we design materials and technologies from a lab, which I'll also talk about. So that's sort of the big picture of what we are trying to do. And I'll talk about 5 different projects or ideas that we are working on, and I'll go through them in a little bit. So the first one, I think some of you have seen this work. So this is thinking about poverty assessment and material deprivation through a basic needs access lens. So moving beyond income and expenditure to figure out how exactly is that households are accessing basic needs services, and how well are we capturing this process. And then another area, we're looking at environmental and equity trade-offs during these energy transitions. And then the third area is on the other end of the spectrum, so thinking about, are there ways to decrease consumption and still maintain high well-being? So it's one of the ideas that came directly from some of the literature that I showed earlier. And a fourth area is digging deeper into material supply chains. So quantifying what I call as shadow impacts. I call them shadow impacts because either it is a design people who are not aware of these impacts, or people consuming materials are not fully aware of the social environmental impacts coming from their consumption. So talk a little about how we are quantifying some of these impacts. And finally, the biggest goal, I guess, being in a materials department, is how do we use all of this information to design new materials and technologies using what we refer to as an absolute sustainability framework. So I'll talk a little more about that as well. So we'll sort of work backwards. So I'll talk about how historically material design has happened. What are the different tools we have in there to develop new batteries, new fuel cells, carbon capture technologies, and I'll show you some of the downsides or some of the tools that we do not have at this point, and how the other four ideas feed into this. All right, so I think a little bit of chemistry here, so please bear with me. So here is an example of what a typical workflow would look like for somebody trying to identify a new material, right? So across the universe of possibilities, so all the atoms you have in the periodic table, if you put all of them together, you get about 10 power 60. And historically, what people have done is you use your human intuition, your training to narrow down on a subset of candidates. You do some modeling, some experiments to see if it works, doesn't work, and you do this iteratively. So some of the biggest breakthrough in human history, so ammonia generation, lithium-ion batteries, a lot of the fracking industry, all of those pretty much worked on this kind of a framework where somebody had an idea, or sometimes accidentally you find a material that works, and then you optimize it, and then you send it to the industry, right? So here's a direct example of how an ammonia catalyst works. So the ammonia catalyst, invented by BASF, Fritz Haber in 1910, used a ruthenium-based catalyst. So what ruthenium does is it's really good at interacting with nitrogen. So ammonia production is you take nitrogen, hydrogen, put them together on a catalyst, form NH3, and then that goes into your fertilizers, and that ended up, saving the world from hunger. So that's the story. And then as material scientists, we're always wondering how a catalyst works and what can we do in order to improve the performance of these materials. So for example, here on the y-axis here is the activity, so it's just how good the material is, and the x-axis is temperature. So you want something that works at lower temperatures. And you see that the ruthenium here up here it has very high activity. And then the material down here is you add some gold atoms to block off some of these ruthenium atoms here, and the activity drops by quite a bit. So the message here is that you can play around with the atomic structure of these materials in order to change the macroscopic performance you get. And this is how the field had progressed for a good few decades, up until more recently, where we wanted to get out of this rut as such of human intuition and develop more physics-based models where you can understand what is going on at the atomic scale without having to go into such precise experiments where you want to deposit gold and change the reaction rates. So a lot of my work in this area has been to use what we call as electronic structure properties. So if you think this is a crystal structure of a perovskite material, these are oxide-based materials. And what we have for these materials is they have different electronic structure bands. So you can see like a gray band here, which we call like a metal band. And we have a red band here, which is the oxygen band. So what we found is that you can change the position of these bands, and that influences the macroscopic performance of a lot of these applications. And so for example, one application here is CO2 capture and conversion. So this is taking CO2 from the atmosphere and converting it into value-added fuels such as methane and methanol, which would then go into either chemical manufacturing or can be used directly as sources of gasoline. And what we showed is that by just changing the position of the band that I showed earlier, you can control the reaction rates. So what's interesting about this is now you have a predictive framework. You don't really have to go in and measure a lot of these properties. The power of this approach is that, hey, you just need to figure out where these bands are. And once you can, then you can do that on a computer, you can look up a database, and it gives you a lot more predictive power than going into the lab and measuring these things. And this predictive approach is quite transferable and powerful. So we've shown this for NOx conversion. So this is in automotive catalyst. So this is the catalytic converter that you have in your cars uses a lot of these catalysts. And we've shown that you can predict the performance of those materials as well using this electronic structure approach. And similarly for chemical manufacturing. So this is for converting methanol into formaldehyde, which again goes into household materials, consumables. Again, here you can see that as you change your electronic structure of the material, you're able to tune your macroscopic performance. So these are just 3 examples that we worked on in the lab. And later we've shown that for a wide variety of unrelated reactions, right? So we talked about CO2, but for other reactions, oxygen exchange. So this is for solid oxide fuel cells, oxygen electrocatalysis, these are fuel cells and electrolyzers, electrolyte decomposition. So this is for lithium ion batteries. So for a wide variety of reactions, we have a really robust way to predict macroscopic performance using electronic structure and atomistic theory. So this is really encouraging in that now you didn't have to do any of these experiments. You could look up tables and predict how efficient your material is going to be. But the downside of this approach is that we are always focused, as you saw, on increasing efficiency of these materials, and we don't really take into account other impacts that these materials can have either upstream or downstream, right? And I'll show you one example of where this gets really tricky. So recently, biomass conversion and upscaling has been receiving so much interest. So biomass upscaling is you take biochar or some sort of a forest produce, and then you try to convert that into value-added chemicals. So for example, you take leaves and sawdust and you try to convert that into gasoline so that you can then use it for more productive applications. So in this particular example, they were looking at 4 different materials and trying to understand which material gives you the highest efficiency to convert your biomass into biogasoline. And what you want is you want a high carbon yield so that you have more carbon to burn, and then less oxygen content. And then you want a material that's cheap as well, right? So in that case, you'd perhaps go with something like a molybdenum carbide here, the 4th one shown here, which is relatively cheap and has moderate carbon content. So usually this is where the story would stop. But recently people have been pushing this narrative and doing more life cycle analysis to see if this is really true once we start considering other impacts. So this is the net CO2 that's produced for these different materials per kilogram of material that's produced. And we see that moly carbide has the highest amount of CO2 that's produced during the synthesis process. Now, as designers, we start to think about the trade-offs. Okay, so you're going to get better gasoline, but it is coming at the expense of more CO2 production. And in a world where there's no CO2 tax, there's no reason why one would not use this material. And it gets even more tricky with trade-offs. Here's an extension of thinking about these trade-offs among other environmental dimensions. So this is looking at smog, ozone depletion, human toxicity, and whatnot, right? And if we look at the green spider here and compare that to the other two spiders, the green one, zeolite, the ZSM catalyst, is the one that's currently industrially used. And it's 3 times as likely to cause cancer for those along the supply chains compared to the other two catalysts. So the trade-off here is that you might get cheaper gasoline, but somebody is thrice as likely to get or be exposed to carcinogenic chemicals along the supply chain. So these are some trade-offs that we are trying to model in the lab. And this one was just during the synthesis process. It's so much more we need to expand in order to fully understand the impacts that the choice of material has on those along the supply chain. And moreover, there's no modeling of what the demand is either. So the field is moving towards that, but I think there's a lot of data and interest that's lacking in trying to model these things. So that's where we stepped in and we started thinking about how do we include both demand side metrics, but also more broader spatial, social, environmental impacts into the way we choose the materials we choose for these applications. So yeah, now I'll switch gears a little bit and talk about how we're thinking about demand. And then we'll talk about material deprivation, overconsumption, and then how do we piece all of this together. So I won't talk too much about this because I think, yeah, you've seen some of these slides before. So how do we really assess if households are receiving the services and the quality of service that they need when they pay for them? So we started looking at income and expenditure, which are the common metrics to assess poverty and material deprivation. And then we said, okay, that's not enough. So we moved on to looking at objective indicators of material deprivation. So we looked at energy consumption, device ownership, and then we wanted to not just look at objective indicators, but the subjective experience that households have when they access these indicators. So we started digging a little more deeper into energy insecurity and how people, even though they have the services, are they really experiencing and deriving the well-being from these services? And then in previous studies, we also looked at if any of these basic needs and material deprivations contribute towards households' overall life satisfaction. So I won't go into all the details of that study, but what we essentially found is that there's a huge mismatch in how existing eligibility for various assistance programs overlap with how deprived households are of these basic needs services. So just to give you an example of energy, what we found was that of all the households that experience energy insecurity, only about 15% of those are eligible to get any assistance through, let's say, LIHEAP or any weatherization programs, and ultimately only about 4% ended up receiving these benefits for different reasons. And the story is more or less similar across the different basic needs. So this is some work that we had done in the past, and where we are going on with this is thinking about the rate of service that households get. So I think Narasimha had done some really cool work recently in this area. So here is one example looking at on the y-axis is the daily hours spent on food production, and on the x-axis is the actual service in terms of kilocalories received. And what they found was that for the more higher per capita GDP countries, you're spending much less time acquiring the service that you're trying to do. So one area that we are really interested in and working on right now is we saw this narrative earlier, and what we want to do is we want to normalize this with respect to the time that people spend in accessing these services. So what is the rate of service that people receive, and what is the underlying heterogeneity, both spatially and demographically, for households to acquire these basic needs services. So that's one area that I currently have a student working on, and I'd be super happy to discuss more about how we are thinking this and how exactly time would feature in some of the existing models that we develop. Right, so we talked about material deprivation. Another cool study that we're doing right now is, well, okay, we know where people are deprived, so how do we direct our efforts? And now, somebody, you have something to say? Sorry. Oh, okay. Yeah. So what are the different environmental and equity trade-offs for some of these energy transitions? And we were particularly looking at heat pump adoption and the different scenarios of distributing a budget. So the origins of this was looking at the IRA, and then they had a fixed amount of budget that they wanted to disperse nationally, and they had the Justice 40 initiative to figure out how does one distribute these funds. And we wanted to come in there and see, okay, what are the trade-offs coming from doing this distribution in different ways. So we had three broad themes. So we had an efficiency theme where we were maximizing a social welfare function. So it's maximizing private gains and public gains together. And then we had an equity scenario where we were directing funds to primarily low-income households. And then we had an environmental scenario where we wanted to minimize CO2 efficiency. That's primarily focusing on just decreasing emissions and nothing else. So we had these three different scenarios, and we wanted to see, hey, where does the money go? Who gets the money? And how bad are the trade-offs between emissions reductions versus giving money to those who deserve the most? And we could clearly see the trade-offs. So here's one spider plot of the different dimensions of these trade-offs. I'll just walk you through a couple of examples. So the pink one is the emissions scenario, and you can see that it's really pointy towards the averted emissions, and it does very poorly among the other dimensions. And on the other extreme, if you look at a low media income scenario, it's the orange one, we do pretty well on hitting low income BIPOC communities, but we don't really do too well along the averted emissions. And then a lot of the other cases fall in between. And there's a lot of room here to play with, which I won't go into. So you can play around with how aggressively you want to target certain communities. And what's more also interesting is that we could have also started looking at where exactly does the money go? Because this is just demographic information, because we also had the geographic resolution to see if it goes to certain geographies. And here's a distribution of trying to figure out where the money actually goes across the different scenarios. And I was focusing mostly on different climatic regions. So that's the one shown on the x-axis. And if you look at the emission scenario again, which is the one in pink, we see that the money mostly goes towards coal regions. This is expected because coal regions right now in the US usually have gas furnaces. And once you replace them with heat pumps, you are going to get a lot of emissions reduction. But once you start doing more equity-based scenarios, we see that the money primarily goes to the mixed and humid regions. So these are Georgia, Kentucky, Tennessee. That's where the money is diverted to once we start targeting based on equity.
So you're saying if you designed the distribution according to those weighting systems, that the money would flow to different places.
Correct. Yes. And this is sort of consistent with what LIHEAP has been doing. So if you look at LIHEAP funding for 2020, it's mostly been focused on the colder states. And what we find is that once you start doing either expenditure or income-based targeting, the money goes down here, which has historically not received.
But isn't the H in LIHEAP, isn't that heating? I mean,
Mhm.
are they trying to support heating? And there
Yeah.
isn't a lot of heating in the.
I think that historically, I think they're focused on heating. Yes.
Well, I think their distribution calculations are based on like heating degree days or something. Zach, you probably know more about this than I do.
Can't they only fund heating?
I think so. I'm not sure.
I thought they only funded heating as well, but I could be wrong.
Yeah, but yeah, Zach, I don't know, but I mean, I can holler at Paul and ask him.
Yeah, Paul
what
would know.
information-
I didn't think they only funded heating. It's low income home energy assistance program, not
Oh,
heating
okay.
assistance.
Okay.
Might be
I'm a
biased
dumbass.
towards heating, but yeah.
They could be, heating is the main use, so I'm not sure.
Yeah, I think de facto, what I had heard, at least historically, is that yes, it's energy, but it pretty much all went to heating. Only recently, maybe has it shifted over to some air conditioning, but I think it was more like a de facto versus.
I think that's right. I
I
think,
think you're
yeah.
right, Ellison. Yeah.
But if you look at financial energy burdens, you'll see plenty of people in the South who have high
Yeah,
energy burden.
right.
It's not that much from heating, but yeah.
Yeah, so this is where we are. And then some of the projects that I'm working on right now are extending some of these ideas to other more blue sky technologies. So working with industries to look at carbon capture technologies and adoption of carbon capture devices. It's probably going to be 50 years or never, but yeah, some blue sky research is also going on in this area. Yeah, so next question is, well, we so far looked at deprivation. Now we sort of move on to the other end of the spectrum and figuring out if there are ways to decrease consumption and what would that look like. So here's one project that I'm working on with the Bass Center for Climate Change and Narasimha as well. And this is the association between life satisfaction and household income expenditure. Here we are trying to see if there is a satiation or a plateau in life satisfaction at higher expenditures, with the underlying argument that beyond a certain point, you're not making gains in life satisfaction, although you're consuming more. And what we found is that, yeah, there is satiation for both EU and US, maybe around $60,000 to $75,000. And in the EU line, as you can see, is much higher than the US line. So for a given, it's unfair to make comparisons, but for a given dollar, you're probably better off in the EU compared to the US. So there's a lot of underlying reasons that we are interested in, but I won't get into too much of details. But once we started finding this satiation, we are like, okay, are there ways to move from here to here? And what would that look like? And what we did was we focused on the high life satisfaction group and started digging a lot deeper into the different consumption metrics and the underlying lifestyles associated with these different consumptions, trying to see if there is a way to decrease or in this case, association between life satisfaction and energy consumption for different lifestyles. So these lifestyles are clusters of different gender, with children, without children, being in a city, housing size. So all of these feed into the different lifestyles shown here. And what we found is that there is a potential argument to be made for about 60% decrease in medium energy consumption and still be in the high life satisfaction bucket, right? So that's the comparison between the yellow and the blue. And digging further, if you take even the least energy consuming lifestyle in the United States and compare that, for example, with Spain, you could see that there's an argument to be made for much decrease in household energy consumption while maintaining high life satisfaction. So I think this goes back to one of the original motivations we had was, can you argue for decrease consumption and still maintain high life satisfaction, and use this as a benchmark for guiding future material demand. So that's one area that we are actively working on. Another one is, well, using some of these ideas to actually go down to the local communities and actually ask them if this is something that they would be interested in, they would be willing to accept a cut in their material needs. So I'm working with a few community planning colleagues here to deploy some of these ideas or even just ask around, run a national survey. So that's a couple of areas that I'm right now extending this study into. Right, so the fourth one is, I think, something that I've just gotten into is measuring shadow social environmental impacts associated with material supply chains. And I think this goes back to, I think, Narasimha, your point about what is out there and what needs to be done in this area. So for example, if you were to look at lithium supply chains, like, broadly speaking, you have 4 different components: so mining, refining, manufacturing, and use. Only very recently have people started looking into spatial environmental impacts. So this particular paper looks at greenhouse gas emissions, water use, land use, associated just with mining in Brazil. And that's the extent to which people have looked at these things. So lithium, again, has received so much interest, right, because of the battery tech, but other materials, not so much. And when it comes to economic dimensions, so it's another recent study which is looking at the effect of mining on the GDP growth in the local mining communities. So that's the one shown in black here. And then spillover effects of communities that are slightly further out from the mining location. And what they found is that once the mine has been established here in 2005, there's some benefits that the spillover communities get. But by the time you get to more 10, 15 year time frame, you don't really see any economic benefits for the local communities. And we are still not even talking about any social impacts associated with the ones we saw earlier with food risks, jobs created. None of those are still being tracked. And so now the question is, well, who's really benefiting and how do we quantify the effects of these mining operations? So for poorer countries, the idea of resource curse is known to some extent, but for richer countries which have more diversified operations, I think it's really difficult to quantify these metrics. And I think that's one area where I've really gotten into. So we started looking at copper and nickel supply chains and using both mining databases, but also other social demographic databases. So using census data employment numbers, and environmental data sets, land use, biodiversity use, soil quality, and making some of these associations across the supply chain. I'll skip this in interest of time. So ultimately, what we want to do is we want to design materials going back to the lab. So we talked about how we really understand the physics really well from an atomic point of view to design these materials. But what we really don't know is how do we include this well-being descriptor so that we have a more balanced approach and we really understand the consequences of the new materials that we design in the lab. So yeah, I call it an undisciplined approach because we're borrowing ideas from a lot of different fields. So I think I started off as a techno-optimist, thinking that technology is going to solve a lot of the problems that we have, but turns out that, yeah, it's a lot more complicated than that. And right now, yeah, we're borrowing ideas from industrial ecology using life cycle analysis, material flow models, and then some of the computational social science that I had done earlier, and then also overlaying a lot of these with environmental policy issues. So they're just sort of dabbing in all of these different areas. And yeah, I think that's all I had for today. So happy to discuss more and get some feedback also, because I'm very new and I have no idea what I'm doing. I didn't say this loud, but yeah, happy to talk more. Thank you. Thanks, Tammy, for giving me the opportunity.
I think it's time for questions or discussion.
Karthik, I love how you pulled everything together into an overarching framework. It's pretty cool.
Yeah,
You have
thank
some
you.
you have some weeds questions in the chat. I don't know if you want to address those first or not. We don't want to go too much into weeds, but
I have to
Right.
go to I have to go to class, so you can ignore my weeds questions. So, but I enjoyed your
Thanks for showing
presentation.
up, Ryan.
Thanks, Ryan. Yeah, good to see you again. Yeah, no, I think that it's tricky to control for weather because I don't know how to do it. As in, should we be modeling for different climatic zones separately so that we eliminate the weather component? Or like, yeah, how would you do it? Because yeah, we've not done it so far.
I mean a combination of CDD and HDD, and just not having ranges of the sum of both, maybe, for example. No? So if
And
moderate
then
climate from
normalize
both
the
respects.
right and normalize the energy consumption to those numbers.
Yeah, because the idea is if you're suggesting to reduce energy use from lifestyle factors,
Mm-hmm.
then you have to allow for some amount of uncontrollable factors.
Yeah, absolutely agree.
I sort of agree. I do agree, and yet I question, like, I don't think people should live in Phoenix, right? I mean, so, but
What's so
there's
great
some
about
amount of
Colorado?
choice in where some people don't have a choice of where they live, but there is some amount of choice that then requires energy use. And I don't know how to disentangle that. Right.
Well, I
Do
mean,
you automatically get a higher allocation because you move to a place that's difficult to condition?
partly this is intractable question. What's underlying it is in your assessment of what behavior change you're looking for, you have to have some guidelines around what you think can be changed and what you think can't be changed.
Yeah,
And
don't
you have
subsidize people to live in Phoenix.
yes, you have to operate within some, and you just have to be transparent about what you're assuming and what you're not assuming. Because you can be very idealistic and assume that kind of ambition, where we just get everyone out of the Central Valley. Don't do agriculture in the
Yeah,
Central
just
Valley.
stop that. Stop that. Just cut it out. Kartik, I had a question about the little spiders that
Mhm.
you had. Um,
Yeah.
and while you're finding them, it's just basically, are you setting the axes so they're equally important? Like there's some kind of boundary number on the very outside.
Yeah, I think they're all equally weighted. I think that's
But your weighting has some implication of value.
right, it does. So the way the spider is set up is that everything's on a score of 0 to 1, right? So you renormalize all the
Mm-hmm.
metrics. So yeah,
Mm-hmm.
you are equally weighting them, and it doesn't have to be that way. But you're right.
But that's
Yeah.
transparent. It's okay. You're considering each of them independently, kind of. So you can look at all the dimensions on their own in the spider diagram.
Yeah.
But how
Yeah.
far out you are is dependent on the normalization. Yeah.
Right.
Right.
That's right.
Right.
That's right.
Yeah.
The comparison is going to be the same, but when one leg of that spider is longer than another one, then it gives the impression that that impact is stronger, and
Yeah.
that strength is dependent on value, and value is sort of imputed by the analyst, right? Like some people would be like, yeah, I don't mind being hot. I just don't want to be, so something else, right? I would rather be wealthy and hot or something. So there's that problematic many aspects of well-being again.
Yeah. Also, in your spiders, just make sure. Sometimes I had to really check to see is outside good or is outside bad.
Right. Yeah. I agree. Yeah.
I know I assumed outside was bad or like higher impact.
It
I can show you.
yeah, it
But
was
I have to totally rethink my impression if it's not.
it's not always bad. Like
Well,
adoption rate
it
is
wasn't
good.
this one, it was the other. It was the other one, like with the
Uh,
metals
Mm,
impact.
Yeah, the metals one, I think that was the one
Yeah, that one. Uh-huh.
but then I realized that the molybdenum, is that what it is bad on all dimensions compared to the green, the
it's
ZSM.
no, it's good on all dimensions. Here, I think outside is bad.
But then that's inconsistent with what you're saying, actually, no? Because you're saying the MO2C is more efficient, but it leads to more carbon emissions.
Mm-hmm.
So it should be worse, but it's on the inside of the green.
I don't know if it has CO2 here, right? I mean, global
It's global
warming.
warming.
Global warming is CO2.
Should be.
Because if you
Oh,
look
this
at
is somebody else's paper. It's not
this is somebody else's.
Mm-hmm. Mm-hmm.
There's something off there because unless it makes sense if inside is bad and outside is good, then it's consistent. All of these are environmental trade-offs, but performance is higher for the orange, but it's bad on
Mhm.
all environmental dimensions.
Right. That's a good story. I don't know if it's
I mean, it would have to be that to be consistent with the
right.
left-hand side.
Maybe they somehow flipped. It's because the numbers go from 10 power minus 8 to 1, which
Oh, well, they didn't have very good reviewers on this paper.
Questions from other people? I have a super general question, but we're almost at time. So, um, so I think you started by saying people may not know what the impacts are. And like in your very early slides, you're like driving what's provided by the household demand. I am skeptical, maybe too cynical, that people may ask for the right things, but it's really the provisioning systems that have to change, is my feeling. Because because you don't examine every one of your objects, right?
What do you mean you don't examine
I
them?
mean, you don't, you just, people keep acquiring things and consuming things.
Mhm.
And yes, you can demand, you can wish that they're better. But a lot of times people are told what to want. And so I don't know that households are going to drive everything. I really think I put the blame on the provisioning systems, I guess.
Yes
It's a
and no.
philosophical debate,
Yeah, I
maybe.
know. Yes. Yeah, I know. Yeah, I agree. I don't know. Yes and no, as in like where does the change come from, or where does the information flow, and who drives the narrative?
Hmm.
Yeah, I need to talk to marketing people about this maybe, but
Well, exactly. It's societally constructed, though, the demand, right? A lot of it. And
It's not
that
just
society has a lot of pieces.
you should watch out for the political ecologists because they jump on this because it was BP who came up with household footprinting and they say they're just diverting attention. But
right.
I think the response is there's agency on the part of households. Maybe you want to distinguish households as political actors versus households as consumers or households as energy demanders, and that you still want to identify well-being associated with households and agency for change, but it's not necessarily responsibility for action you're focusing on because that's more complicated. So yeah, I think you should, especially when you get into this, the environment, the shadow analysis. When you present at conferences, if there are political ecologists in the room, you just have to be careful about what you're meaning by what you say.
Umbrella.
'Cause they'll literally jump on you.
I see.
But I think there's hooks in all of those actors, right? That people, entities, stakeholders, and so on they each have a different role to play. I think part of the danger is in assuming that the power lies all in one place or that large power lies in certain places, without holding the rest of the system accountable.
Yeah, I agree.
Okay,
Yeah.
we're a little over. I'm eating into my meeting time with Kristen. Thank you all for coming. It was great to see everyone again. And thanks for joining our group, Zach. You should have been there all along, but you're welcome now.
Well, thanks for having me. Good to see everyone. Bye.
Thank
Take
you.
care.
Bye. Thanks, Karthik. Bye.